And with that, I'm going to stop the updates and prepare to welcome Professor Weck, who's coming back. Hopefully you all remember him from our very first class. And he's going to share a set of perspectives with us today about the space economy and systems as well. So Professor Weck, welcome back, and thank you so much for even more of your time. We're really excited to have you today.
Thank you, Ariel. Fantastic. Well, thank you. And so we have an hour, and then I think you have a panel session, a very exciting panel to follow at 10 o'clock. So my goal today is to share with you a perspective and some work that we've done that already dates back a couple of years, and was funded by NASA. And particularly, NASA has an Office of Space Development, a program called Economic Research for Space Development. It's the Emerging Space Office that Alex McDonald started. And I don't know if Alex is on the call or if he's going to join at 10, but I do want to acknowledge him and the NASA support for this work. The basic idea here is that NASA traditionally has invested in human and robotic space exploration for scientific purposes, and not really looking at what does it take to develop and support a commercial space ecosystem, that is technology-based. And so the motivation here was to develop a commercial space technology roadmap, and out of it, decomposing this emerging space economy into its different sectors and subsectors, and better understanding how these sectors connect to each other. And I do want to acknowledge, so the work that I'm showing you here was done primarily between 2017 and 2018, a couple of years ago. And I think there's some updates that were done since then, but the bulk of what I'm showing you today is from 2018. I do want to acknowledge the team that worked on this beside myself: Dr. Afrin Siddiqui, who's a research scientist here in Aeroastro; Matthew Moragues, who is a doctoral student. Actually, he's going to defend his thesis probably in June on the topic of in-space manufacturing. Alex Trujillo, also a doctoral student, who will defend as well in a couple months on the topic of model-based system engineering. George Lodos, some of you might know, is working on human settlement, particularly for Mars. And then Mehak, who's on the call, who did participate very actively and contributed greatly to this work while she was still at Wellesley College. So the basic story here is that the new space economy is really at the very beginning and is emerging. And if you look on the right side of this chart, the dominant technology development model starting in the 1960s up to the 2000s, and we're just mainly talking civilian here, NASA, but I think if you put the DoD, the Department of Defense there, you would get a very similar picture, with a multiplier in investment, which is significantly above what we invest in civilian space. We just don't often talk about it as much. So we have these technology areas. There's 15 of them, and basically the any commercial companies that are involved are contractors. They're developing these technologies and missions and subsystems as direct contractors to NASA or other federal agencies. What's new here is the left side, shown primarily in green. And the idea is that, there are more and more commercial activities happening in space. Earth imaging comes to mind. Traditionally, space telecommunications, like DirecTV, those were the money makers in space and the only money makers in space, but it's really diversified. So the whole Earth imaging industry, the launch industry, the sectors that I'll mention in a minute are really emerging. And ideally, what we have now is this much richer ecosystem with drivers of value chain growth dynamics on the left, and still accelerating pace of technology development driven primarily by science on the right side in blue. One of the interesting questions is, when do we know that a real new space economy exists or has really emerged? And my answer to that is very simple. If you're a company in this ecosystem, so one of those commercial space companies, can you see my pointer, by the way? Yes? Okay, great. So if you're one of those commercial space companies where I'm pointing right now, the day when more than 50% of your revenue comes from orders that you receive from other commercial space companies, and less than 50% comes from direct government contracts, that's when you know that you're part of the new space economy. If 90% or 80% of your revenue still comes from the right side, then you're not yet part of the new space economy. And this happened to a lot of American companies. The question was, are we an American company or are we a global company? The day that more than 50% of your revenue comes from exports or from sales overseas, that's when you know that you've become an international company. It's a very, very simple answer in my mind. So the methodology that we followed here was the following, and it looks a little bit complex, so I apologize for the complexity of this chart. But the logic, I think, is think of supply and demand. On the upper left of this chart, you see the space economy decomposed in its sectors, and that's what we do on Earth, right? We decompose our economy into different sectors: production, services, agriculture, etc. And what we did here is we decomposed the space economy in 9 major sectors and 29 subsectors. And I'll go over those in detail in a second. So market sectors and then subsectors. And there's obviously interdependencies and interactions between these subsectors. And then on the lower right, you see the key technologies that are necessary to enable these sectors. And so for each of those key technologies, we looked at the dimension of time, what's state of the art, what can we do in the near term, what can we do in the long-term future. And then in the middle, the key is who is an active player in that commercial space economy, actually going and looking at companies and when were they founded? Are they mergers of multiple companies? We see consolidation happening. Redwire is a good example of a company that's been acquiring smaller companies. What is their vision? Or what is their thrust and subthrust? How can we quantify what's happening in terms of figures of merit, trends, and targets, realistic targets for these figures of merits? And then what are the actual customer needs that they're satisfying? And finally, in the upper right, what are the products, goods, or services that they're offering? Which of these are still active? Which of these are retired? And which of these are planned and on the horizon? So basically, by filling in this framework step by step, you can build a pretty clear picture of what's happening. So what I just showed you is on the left. And the results of that, you can then store in a database, which is what we did. We call it the CSTR database, Commercial Space Technology Roadmap Database. It also includes patenting activities and trends. And then the outputs from this particular effort were the methodology itself, the decomposition of the space economy into these subsectors. And we did a few case studies. We just didn't have enough time and to study all the sectors. So if any of you are interested in this, there are plenty of sectors to really analyze that we haven't even touched. And then finally, the recommendations to NASA and to industry. And so hopefully you had a chance to look at the pre-reading, which are one report is the methodology, and then the other document is the case studies that we did. In terms of the methodology for developing these roadmaps, we essentially adapted NASA's technology roadmapping development process that they had developed, in particular the one for the aviation industry. And the only differences we did, there's 14 steps here. The only differences were that instead of mission classes, we used the space economy sectors. Instead of the design reference missions, which NASA typically does, we replaced it with business models. Instead of government investment, we looked at private investment. And instead of NASA priorities, which you often find in the decadal surveys, we looked at industry priorities. But for the other steps, we pretty much followed the standard NASA technology roadmap process. Okay, so enough about methodology. Let's look at some of these sectors. And I'm going to present to you 3 sectors that we looked at. And then wrap it up with looking at the intersection of these sectors. So the 9 sectors are shown on the left here in this table. So first of all, space transportation and access. Unless you can actually get to space and stay in space and move in space physically, you have no space economy. So launch services is absolutely essential. And it's a very exciting sector. And it's one of the sectors that we looked at. And Mihak, if I'm correctly remembering, this was actually your sector that you did. So feel free to chime in at any moment here. Number 2, spacecraft development and manufacturing. Number 3, we often don't think of it in terms of being part of space, but the ground sites. So both spaceport tracking of space objects as well as satellite operations are critical. On-orbit services, this is probably one of the rapidly growing sectors now. In-space manufacturing, on-orbit servicing of spacecraft, and then orbital debris tracking and removal systems. 5, this is, like I said, this is where we've made money in space before, telecommunication services, fixed satellite, satellite service, and then mobile satellite services. So Starlink, for example, would fall into this sector. Navigation and positioning services, including GPS, GLONASS, all of the international systems, Galileo, and so forth. 7 is remote sensing services. 8 is a sector that doesn't really exist yet as a market, but a lot of people are looking at it seriously. It's resource extraction in space. And so there's the surveying and mapping and mining part. Sorry, there's the surveying part first. Then there's the extraction and processing part. And we broke apart, we distinguish here between water and volatiles and extraction of metals, minerals, and ores. And so Jeff, MOXIE, which you've been spending a lot of your time on MOXIE, would fall into subsect 8.2. That's where I would put MOXIE. You know, if you could sell your oxygen.
Ali, what about what do they call it? The metal oxide extraction. You know, where you liquefy the metal oxide and electrolyze it so that you get both a usable metal and oxygen. You know, that's
yes.
Hathaway has done a lot of work in that. So it's not. Sometimes you can get both. That was the only point I wanted to.
Right. I guess it depends which one is the primary, resource that you're going after, and which one is kind of the byproduct. But I would put like, hydrothermal reduction or electrowinning in particular, where you essentially melt the regolith. I would put that into 8.3.
Okay. Yeah, we don't have to, formally decide it now. I just wanted to bring up that there is kind of a hybrid situation where you get both. In fact, Don, when I was talking about, and when he had proposed doing this on the moon with the liquid metal extraction, he said that, he was looking at it for processing ores here on Earth, and he was getting all this oxygen as an unwanted byproduct. And then he heard that NASA wants oxygen. So that's sort of how it started.
Yeah. And no, it's a great question, Jeff. And, it's true, I think, on Earth, of course, resource extraction on Earth, it's, mining, oil and gas exploration, etc. It's a huge sector. And if we're really serious about staying in space and operating space long term, we're going to need that. And it's very early days, but it's sector 8, that's for sure. And then number 9 are supporting industries. So, companies that make robotic systems, research and development services. And then there's a huge industry around data processing, storage, dissemination of space-related data. And then not to forget the financial industry. So 9.4 is insurance, the insurance industry for space. And, you know, so that's the 29 subsectors.
Ollie, one other question. Where would you put the? It hasn't started yet, but space tourism is something that we've talked about in this class. So, I mean, it might go under transportation and access, I suppose. But have you thought of where you would put that?
Yep, space tourism is in there, and it's generally in Sector 1, and so you can see it's actually mentioned explicitly here under 1.1. You see that? Exploration/tourism.
Oh, okay. I didn't see the fine print.
Yeah, so it's there. Okay, so the subsectors that are boxed in bold are the ones we looked at in detail, and the ones in dashed we looked at somewhat in a cursory fashion. So we'll talk about launch, industry, in-space manufacturing, as well as Earth imaging and sensing. And so we did a case study on each of these. What is also very important is that, you know, this only happens if you have the right technologies at the right level of maturity. And here we did not reinvent the wheel, but we basically tried to map as close as we could against the existing NASA 3-level technology taxonomy. And so this is an example of what it looks like in propulsion systems, which is technology area 1. And then you have level 2 as liquid cryogenic, liquid storage, solid, and other. And then you get down to 1.1.1, 1.1.3 is LOX methane systems, and so forth. So it's quite detailed. And we mapped it, as you will see, against this detailed 3-level technology decomposition. So let's talk about launch services. This is our sector 1.1. I think it's extremely exciting what's happening in launch. You know, the launch sector was kind of sleepy. You know that most of our launch vehicles that we used in the 70s and 80s into the 90s were basically derivatives of intercontinental ballistic missiles. They weren't really designed from scratch as human or robotic space launch vehicles. They were really there to carry nuclear weapons. And you know, I think it's extremely exciting what's happened. So 3 pictures here, Rocket Labs. This is the Electron. Virgin Orbit, we had a great presentation a couple of months ago by Virgin Orbit. They had their first successful orbital deployment. And then we have Blue Origin with New Glenn. And so there's a huge amount of activity happening in the launch sector. And that's very exciting. The strategic thrust in this sector is to provide cheaper, safer, and more timely transportation from Earth to space while meeting all of the payload needs. And so that can be decomposed into strategic subthrusts, launch cost reduction, improved safety. This is very important, increased launch cadence. So how many launches per year can you actually support? This is where a company like Astra, you know, with their really small launcher and their distributed launch sites, is going to make a huge difference. Improved responsiveness. How long is the delay between when you sign a launch contract and when you actually get to launch? And then, you know, meeting the payload needs. The big question here is what will be the relative market share of, particularly for small satellites, taking a ride as a secondary payload, which is really the dominant mode right now. You know, the big disadvantage of being a piggyback launch is you do not get to choose your insertion orbit. That's a huge disadvantage, even though it's less costly typically, versus having a dedicated small launcher. Here's the mapping of what's happening in the launch industry in terms of technology investments. And you can see some of the key players, excuse me, Blue Origin, Orbital ATK, which is now Northrop Grumman, Rocket Lab, SpaceX, and then ULA. And so you can see some of these areas are very active. So everything in the area of launch, you know, so new engines, excuse me, structures and mechanisms, thermal avionics and GNC, a little bit less on the ground segment. And you can see in some of these areas, there's only 1 or 2 players. In some of these areas, everybody's investing at the same time. The other interesting thing in the launch sector is looking at the launch cadence, how many launches per year. Particularly here, Mehak, correct me if I'm misstating this, but these are commercial launches. These are not all launches. These are just commercial launches. So for example, a NRO, National Reconnaissance Office, security payload launch would not be included here. And so what you see here is a lot of different colors, because there are, in fact, a lot of providers, and there were a lot of providers, but the colors change over time. And the dominant color now is purple, which is what? Well, SpaceX, basically. Falcon 9 has just really taken over such a large part of the market. And you can see that we had an uptick, and then we had a real downturn in the number of commercial launches between the late 90s and 2011. 2011 was the low point. And then since then, it's been going up continuously. And the last data point here is 2017. So if we updated that with 18, 19, and 20, it would continue to go up. And it will continue to go up. There's a lot of discussion on cost, per kilogram to low Earth orbit. This is a reference orbit, a low orbit, 185, 28.5 inclination orbit, sort of to put things on equal footing. And a real game changer here was the COTS program. This is the NASA Commercial Transportation Services contract. And pre-COTS, the estimate was about $13,600, so $13,600 per kilogram to launch to low Earth orbit. And since then, that average has really dropped a lot, down to about 5,600. If you specifically look at just the Falcon 9 or Falcon Heavy, you see that here, that's actually dropped to $2,000 to $3,000 per kilogram. So, Elon Musk promised us, I don't know what, he made a lot of promises, like 100-fold reduction in launch cost. That has clearly not been accomplished, but it's getting close to a 10x reduction, right? Somewhere between 5x and 10x. We're not quite there yet, but we're starting to approach particularly with Falcon 9 and the reusing of the first stage, we're starting to approach $1,000 per kilo, which is very impressive. But it took more than a decade to do it.
And then there's Starship coming along, which is, when he gets it to work, it's going to be probably another order of magnitude if it works as they expect.
Yeah, that's right, and that's a great segue, Jeff, to this chart, which is kind of the look ahead. So we're already in 2021. Remember, we did this chart in 2018, and what's really exciting, I was looking at this last night. So Starship, of course, is BFR, right? BFR is doing hop testing, some more successful than others, but this is a check mark. It's really, really happening. And the selection of SpaceX for the HLS lunar landing system is a big deal. And so this is definitely a check mark here. Blue Origin working on New Glenn. New Shepard is an active system. New Glenn is under development. I would put a check mark here as well, but they're two very different companies and working at very different paces. But this is absolutely active. SLS, honestly speaking, is a very painful story. I don't want to go too far in my comments here about SLS, but it still hasn't had its first full launch, but it will happen. But then the longer term future of that system, I think it's something that it's more in the policy realm than in the commercial, to be honest. ULA is developing Vulcan, and this is also going forward. So this is a check mark as well. I'm not as up to date on what Northrop Grumman's plans are for the follow-on to the Antares, which launches, for example, from Wallops. But we had a chance to go see that launch pad last January, and clearly that's an active system. And then Virgin Orbit turned from green to blue and is now an active system. So all of the players here in the last 2 years have made progress and are turning their development programs into active systems and have orders for them. So this is extremely significant. Let me switch gears to Chapter 7.1, which is Earth imaging and sensing. This is, of course, a sector that in the past was dominated by governments, military intelligence, but also commercial land use imaging. Landsat comes to mind. But what's new is commercial players that are now offering this imagery for sale. And the prices for this imagery are becoming much clearer. We have a current project with a company called LabSphere in New Hampshire. They're specialized in calibration services. So we're quite knowledgeable these days about what are companies charging per square kilometer per image as a function of resolution, whether the image was taken as part of regular monitoring or whether it was an on-demand image that you ordered. Those are more expensive, obviously. But there's many uses in agriculture on the left. Disaster monitoring. This is a tsunami before and after. And then on the right, you see a high-resolution image of a port. And you can see these different, coal, different commodities being loaded and offloaded off ships. And so the financial industry has a great interest in understanding what's happening at our ports, what commodities are being loaded onto what ships, and where are these ships going. And if you even only have a few days notice of what's happening at your competitor, you can monetize that knowledge. And so they're a big consumer of satellite imagery now. Strategic thrust is to cost effectively develop, deploy these imaging systems at high resolution, more frequent, large coverage, more responsive. And it's a growing base of government, military, and industry customers. Subthrusts are on frequency, resolution, coverage, responsiveness, and cost effectiveness. And then you see the figures of merit. Some of these are bolded because they're more important than others. So revisit time, spatial resolution, and then how long do you have to wait to get your image once you order it? One thing that I think we didn't include that I would include today is the quality of the imagery, particularly with respect to radiometric calibration. So we had radiometric resolution here. What does that mean? It means colors. It basically means how many grades of colors do you have in your different spectral bands. And radiometric accuracy means how close to true color are the colors that your imager is capturing. And so here we have also significant dynamics going on in this market. Remember that all players that are identified here, we only, by the way, in this work looked at US companies. That's a limitation that we agreed on with NASA when they funded this work, because we wanted to focus on active US players, but you could certainly expand this to a global perspective. You do need a license if you do commercial imaging from space from NOAA. So all of the companies listed here have active NOAA licenses. And so you see their key product. You see, for example, Planet, which is growing and is doing well. Digital Globe, which has now been renamed or bought by Maxar. And so we see some definitely a lot of consolidation has already happened. And I think we're down to 2, maybe 3 major players in the commercial imaging sector. Again here, you see the flocks, which have now been deployed, different generations of flocks. Planet is an amazing company in terms of using agile approaches. Worldview, so this is Digital Globe, now Maxar. And then we have a bunch of smaller players. Some of these have now been merged or bought. And so this is quite a dynamic place. And then when you look at the number of patents as well, in the area of Earth imaging, Earth observation, remote sensing, geospatial data analysis, the number of patents have also gone up steadily over the last decade. Key technologies to look at are the imaging payloads, panchromatic, this is black and white, multispectral, hyperspectral, and then probably the most challenging technically is SAR, synthetic aperture radar. Why? Because you can get 3D structures. You actually get 3D images instead of just, flat pixel images. Targets definitely to be below 1 meter resolution in multispectral. Panchromatic resolution below 30 centimeters, sub-daily revisit times, every hour an image or every 90 minutes, and then high data storage in the terabit, kind of quantities of data. By the way, all of you at MIT, you should know that we now have an umbrella license with Planet. So if you want to get an active account on the Planet Explorer interface, you can at no cost. MIT Libraries, the GIS lab pays for that. And the last 2 years we've had it, and we're significantly under our quota. So there's a lot of opportunity for you to learn more about Earth imaging. And you can see here the technologies that are being invested in as well. So the trends in terms of ground resolution versus launch year, we're actually starting to approach the physical limits of diffraction imaging from space. So the aperture size becomes sort of the critical factor. And of course, the orbit that you choose. This is a plot of refresh frequency. This is not how many images per day, essentially. So if you're at the 1.0 line, it means you're getting 1 image per day, the location of interest. 10 means you're getting 10 images per day. And then ground resolution is, 1 meter versus 10 meters versus 100 meters. So a lot of the, what's happening essentially is we have a lot of free imagery, like from the Landsat program, which is low revisit frequency, an image every 14 days, and a fairly high resolution or low resolution 30 meter pixel size, but very high radiometric quality. And then we have this market up here in the upper left, which is very frequent images, but maybe the quality isn't quite there yet. Okay, one more sector, and then we'll have a discussion. The last sector I want to tell you about is in-space manufacturing. And this has been Matthew Moraga's main research area. This is also a nascent sector. So two companies that I'm showing here. One is Tethers Unlimited, quite an innovative company. You see this spacecraft. It looks kind of like a spider. So it's called Spider Fab. It's essentially a bio-inspired design, like a spider building its spider net, building essentially a large reflector array. And then on the right, we have Made in Space, which was just bought by Redwire. And they have several 3D printers now on the International Space Station. And so here, the strategic thrust is to fabricate components in space with performance and cost reduction compared to Earth-fabricated products. And to do this with reasonable size, weight, and power. And so the figures of merit are, well, what is the actual cost, excuse me, of the in-space manufacturing facility? Are there any cost savings relative to launch? Because remember, if you manufacture in space, you do not need to survive the launch loads. That's really a big deal. And you don't have to fit inside of a fairing. And so you can start making these very large, very extremely lightweight structures. So what is the size, weight, and power of your manufacturing equipment? What production rate can you support, units per year or kilograms per year? And then finally, what's your operational lifetime? And so here we're also seeing both historical efforts and new efforts come to fruition. This chart shows you facility power. This is a big limitation in space for manufacturing is, power. How many watts of power can you actually use in your manufacturing facility versus the mass of the facility itself. So on the right side, you see this was the Northrop Grumman Beam Builder project. in the 1980s, a triangular truss. And you see it was a very heavy facility, like 8 tons, using, you know, about 800 watts of power. We wouldn't do it this way today. We would do it in a much smaller way. So Tethers Unlimited has a triangular truss production, the so-called trussulator concept. This fits into a 3U system. It's obviously a much smaller truss, but you know, it's extremely lightweight and compact. Similar things than what we saw in other sectors. The patenting activity is going up very rapidly, especially since 2010. Made in Space is really a key player here. They have a lot of projects. The Archinaut project, now relabeled OSAM-2, is ongoing and will fly in the next couple of years. And then government investment in space manufacturing, especially since 2012, 2013, is really growing very rapidly. And you see the different players here in different colors. Again, Made in Space and Tethers Unlimited, especially from a US perspective, are probably the leaders here. And then what are the key technologies that are being invested in? Robotic arms. Interesting area, recycling of plastics in space, particularly on the space station. Additive manufacturing with composites, and then, of course, additive manufacturing with plastics. And then here, if you want to see it again by which of the players, we can see the ones I've already mentioned. So recycling of plastics. This is another interesting area, construction with in situ resources. Planetary surface construction using regolith is an example. And then all kinds of additive manufacturing in space with metals for electronics and with composites. Okay, so let me wrap it up, and then we'll have a discussion. So the high level findings are that you know, people talk about this new space economy, and it's really but we're not at the point where more than 50% of the revenue comes from orders from other space companies. It's still heavily dependent on government investment, whether that's NASA or the DoD or NOAA. But the US government is a major investor in the space economy, and so it requires new kinds of public-private partnerships. We've created a dynamic and insightful database that probably needs some updating now. We've looked at the space economy in terms of the sector breakdown, and then there's a lot of work to be done on characterizing better the interdependencies among these sectors and subsectors. And so on each of these, we found different models for these public-private partnerships. There's a whole bunch of Space Act agreements. There's the Small Business Innovation Research Program, which has been around a long time, but is increasingly looking at these technologies for commercial space, and then technology transfer, which is the STTR program. This is the schema for the database that we put in place. It has 13 major tables. So the technology areas, the name of the organization, the sector and subsectors, the products or services they're developing, the technologies that are enabling, the technology to product mapping, the figures of merit, and then the mapping of the figures of merit to the sub-thrusts. And so in total, we looked at these 9 sectors and 29 subsectors. We analyzed 3 of them in depth and 2 of them in a shallow way. So this shows you that 24 sectors, subsectors, we didn't even analyze in detail yet. So any of you that are interested in collaborating in picking some of those subsectors, whether it's a semester project or thesis, you know, we'd be delighted to hear from you. We identified 61 organizations with 134 products, about 150 technologies, and the date range that we looked at was 1981 to 2018. But we did do a little bit of work since then, particularly with Europeans. So we've added some European companies since then. The final thing I want to show you is, I think, very cool, and this is where a lot of work is needed. So if you do an n-squared diagram or a DSM of these 29 subsectors, you essentially get interactions between sectors. And think of the interactions in terms of what is the key driver? Is it price? Is it capacity? Is it schedule driven? And some of these sectors, you see the launch sector has connections with almost every other sector. So unless the launch sector is really healthy, and it seems to be quite healthy these days, nothing else really matters. And then you have all the companies that are in spacecraft satellite design, manufacturing, integration, and testing. That's also a key sector. On-orbit servicing is much more, it says future impact here, is still very early on. Resource extraction is still early on. And so there's a lot of work to be done to fill in these sector interactions and quantify those interactions. Okay, so limitations, plenty of limitations. We limited ourselves to publicly available data. We didn't use any confidential information or private data. We probably missed some sectors, and I think this work was well received. I wish it wasn't just a 1.5 year effort. I wish this would be a 3 to 5 year sort of slowly funded effort. But we're definitely keeping it going, and looking for your feedback on this. So with that, I will probably stop it here and look for your questions.
Thank you, Ollie. I think you've given the students a really fantastic foundation for the roundtable in the second half of class as well, across several sectors that will be discussed in the context of evolving into a lunar cislunar economy, if there can be that growth. Because we're on a new platform today, class, I just like to invite people to directly unmute themselves and ask a question for Professor Weck, rather than trying to do it through the chat.
I had a question for Ollie. Are you going back to that chart that you showed at the beginning, showing how like NASA and commercial companies work together? Do you think there's room to, I guess, like how would you incorporate academia into that chart? Do you think it would be like a whole separate area, or it's sort of like slots in somewhere?
No, I think academia isn't called out explicitly here, but I would put us somewhere, honestly, close to the middle of the chart, in the sense that the role of because academia, we're really working on low TRL, TRL 1, 2, 3, 4 kind of technologies. So seeding ideas for new technologies that are too risky, perhaps, or not well understood yet, new kinds of physics. So that's one area, and so that definitely has a accelerating pace of technology development, so having an impact here. We also have, I think, great examples of students who start their own new companies, right? Like an example would be Adam London and Astra, right? He's a graduate of the Air Astra department. And so Axion Systems is another example. And I should tell you that we're starting a new certificate program this fall in Air Astro on aerospace innovation. And it's specifically, it's not just for space, it's also air, drone companies and so forth. But the starting of new ventures is absolutely something that academia can do and is doing. And so we're going to be offering this new certificate starting in September for people who, want to start their own companies, or at least want to learn about how it's done. And then the third role that academia plays is to, provide the workforce of the future, both for NASA and these commercial space companies. Does that make sense, Becca?
It does. Thank you, Ollie.
Okay.
Until we have another question from the class, I'll take instructor's privilege here and ask Ollie a question I've had for a while. I'd love to hear, Ollie, what your thoughts are on, do we need an analysis like this for lunar propellant or lunar ISRU? We've heard a lot of contrasting perspectives. So Martin Elvis will tell us the space resources are really constrained. Tori Bruno and the ULA analysis comes in and says, paints this very rosy picture about the amount of in situ mining that we could do, and even having a national reservoir, and really thinking about the future of this series of depots that ULA wants to pursue. I'd love to hear your thoughts on what would it take to get us actually an informed answer and an analysis around the commercial possibilities for lunar mining, particularly for propellant.
This is definitely a really interesting topic. How should I say this? We published a paper back in 2016. I don't know if you remember, on if you could mine oxygen on the moon, because the lunar gravity is, only 15% of Earth's gravity. If we could actually mine oxygen on the moon, whether it's from the regolith, like Jeff was talking about, or from subsurface ice, that oxidizer could be brought into orbit, into a fuel depot, and we could drastically reduce the amount of mass that we need to launch from Earth to go to Mars, for example. So it's the detour through the lunar system, and and I think the math is solid, but we got a lot of pushback on this conclusion that you could save 68% of mass because of, it's all about the assumptions you make on those figures of merit for the technology. How much oxygen or any other resource you want can you produce per kilogram of plant mass per year? And initially, right now, MOXIE is doing very well on that metric because you have the atmosphere. If you have to dig things out of the ground, heat them up, process them, separate them, it takes a lot of equipment. And so the point I'm trying to make is there's a break-even point at which the technology yields enough resource per unit of investment that it becomes advantageous to use the local resource. Now, whether there's a market for that, a whole nother question. Before there can be a market, you have to show that even with a non-market situation, it's advantageous, at least along one of the dimensions, compared to bringing everything from Earth, which is what we do now. And so, Jeff, I don't know if you want to comment on this. We had this discussion before on we call it ISRU productivity, kilogram of resource produced divided by kilogram of plant mass per year. Jeff, I don't know if you want to comment on this for MOXIE.
Well, it's a little, harder when you have something like MOXIE, which does not run continuously. So we will be collecting the total amount of oxygen that we produce, and then we can figure out how long it took to produce it. The other question is, what do you use for the mass? Because of course, MOXIE is sitting in there, 15 kilograms or so, I think, but it needs electrical power. And so for any ISRU system that uses electrochemistry, you always need a lot of power. So you really have to take the mass of the power system as well. So yeah, we'll be able to work out those numbers. I'm not sure, since MOXIE is not a continuously operating system, it doesn't have quite the same significance. But what you say is absolutely right. The other thing, of course, in terms of the economic value of a system, particularly for the moon, I mean, as the cost of launch from the Earth continually goes down, the economics of ISRU on the moon change. So, ultimately, if it ever becomes cheaper to launch oxygen from the Earth than produce it on the moon, then you don't need the ISRU. So there's a lot of factors involved.
No, absolutely. And, if you want to draw an analogy with the, on Earth, it's the energy industry, right? Distributed renewable energy like solar PV, wind and so forth, competing against oil and gas, fossil fuels, which is a much more centralized system. The crossover point where one wins over the other shifts dynamically, and this will happen in space too.
Yeah.
Great. I think we have time for one more question before we'll take a short break between the hour of lecture and then the roundtable that we have at 10 a.m. One final question anybody would like to ask?
Okay. How do you see policy affecting sort of these flows that we see in this diagram?
Oh, yeah. Well, yes, absolutely, at multiple levels. So one form of policy is to require permits the permitting process. And so there's a lot of discussion about space law having changed, right? We're going to go make claims on resources on other planets. That's a whole discussion. Clearly, launch permits are required. Launch sites need to be permitted by the FAA primarily. The commercial launch office within the FAA. There's also the priority setting in terms of technology investments by NASA, by the Department of Defense, the pecking order, so to speak. Who gets most of the investments? Should we invest more in propulsion or remote sensing? So the investment policy is also going to be critical. And ITAR, ITAR and export control is a 800-pound gorilla here as well. If you really, like I said, when does an American company know that it's become an international company? And I said to you, it's when more than 50% of your revenue comes from international customers. That's not so trivial in some of those sectors, right? That's why, a company like Lockheed Martin, Lockheed Martin has a lot of international revenue, but the dominant source of revenue is domestic. It's the US government, 85%. And so if you want to really be a true commercial player, you have to be able to sell your products globally, and there may be restrictions on that, depending on what the technology is. And so, Kristen, I don't even know where to start because there's so many layers of policy influence here. It's hard to even list them all.
Yeah, that's totally fair. I guess I just wanted to see your overview. So thanks.
Okay.
Wonderful. Well, Ollie, thank you so much for coming back to class a second time. Thank you for sharing the pre-read with the class as well. So if anybody did not take a look at it prior to class, I really encourage you to dig into it. There's a lot of really fantastic insights that can inform your mission concepts as you finish up your CDR for the class, and also just inform your understanding of the space industry, thanks to the great work that Ollie's lab and our own Mehek Sarang had contributed to in the past. So thank you again, Ollie, for coming.
Thank you, and I really wish I could stay for the panel, but I can't. So hopefully recording it, and I'll be watching it offline. Thank you.
Thank you.